Okay, let's jump straight into it. We are summarizing the paper, EditThinker, Unlocking Iterative Reasoning for Any Image Editor.
All right, so for the 60-second summary, the whole point here is moving image editors beyond just, doing what they're told once.
Right.
This paper introduces a framework they call EditThinker. It's designed to fix the big limitations of single-turn models, the ones that fail as soon as your prompt gets a little complex. The core idea is this think while edit loop, which is meant to copy how we think. First, you critique the last result, then you refine the instruction based on what went wrong, and then you just repeat.
So it's an iterative loop.
Exactly. They implement this with a multimodal large language model that's trained with both supervised fine-tuning and reinforcement learning on a new data set they built. And the best part, it's a wrapper. You can plug it into any existing editor-flux.1, Quinn image edit, whatever, and it just works, especially on tough stuff like spatial or causal reasoning.
Okay, let's unpack that. Because if you're an ML engineer listening to this and you're struggling with prompt adherence, this paper is basically telling you why. Your editor is a reactive executor, not a reflective thinker.
That's the perfect way to put it.
So we have to start there. Why is single-turn editing hitting a wall? Aesthetics are pretty much solved, right?
They are, yeah.
Yeah.
The current state-of-the-art models, they're all fine-tuned on these huge, powerful foundation models. The images look incredible, photorealistic. The whole game has shifted.
To what?
To precise instruction following. That's the new frontier, especially when an instruction has multiple parts or some kind of logical dependency.
And the problem is that these models have to do everything at once. It's this coupled one-pass system. They have to understand the prompt, plan the visual changes, and generate the content all in one go.
It's just too much.
Yeah.
And because of the randomness, the stochasticity inherent in these models, and the complete lack of any deliberation, they have no chance to self-correct.
No do-overs.
None. They can't stop, look at what they've done, and say, hang on, that's not quite right. The mistake is just baked into the final output.
And we've all seen the results. The paper points out these classic, really frustrating failure modes, like losing subject identity.
Oh, yeah.
You ask it to animate a cat, and it keeps the cat, but it loses the specific fur texture or the pose that made it your cat.
Or the semantic failures, which are just poison for any real-world application. You try to replace a background, and suddenly the text on a street sign in the foreground is just gibberish.
It looks right visually, but it's semantically a total failure.
Exactly. Then you have coherence. The paper gives a great example. Change an umbrella's color to brown. The model does it, but the brown looks like a flat sticker pasted on top. It doesn't match the lighting, the texture.
It's not integrated. The model can't think, okay, the color is brown, but the texture is wrong. I need to refine my own internal prompt to say, rich, textured brown leather.
And that inability to articulate the problem is the missing piece. Even existing RL methods, they just give feedback after the fact. They score the final image, but they don't fix the flawed logic that created it.
Okay, so this is where EditThinker comes in, and honestly where it gets really interesting. They address this by completely decoupling the process.
Right. They split it into two roles. You have the thinker, which is for judging and reasoning, and you have the editor, the existing diffusion model, which is just for execution.
The thinker is the director, the editor is the camera operator.
Perfect analogy.
Yeah.
And that thinker is an MLLM that runs this critique, refine, repeat loop. And to do that, it needs a lot of context.
And that context is what drives the iteration. So at each step, let's call it step T, the thinker isn't just looking at the original image and the original prompt.
No, it's also looking at the image that was just generated in the last step and the instruction that created that image. It sees the whole history of failure. And that input allows it to analyze what went wrong and then generate three things: a score, its reasoning for that score, and most importantly, a new refined instruction.
So the thinker is basically acting like an expert prompt engineer on the fly. It just keeps tweaking the instruction until the editor, whichever one it is, can finally get it right.
That's a great way to think about it. And they prove the concept works by using GPT 4.1 as a kind of expert thinker first. And what's wild is that just by doing that, without even fine-tuning the editors, they saw massive performance boosts across the board.
That's incredible. It shows the bottleneck really is the reasoning, not the image generation itself.
It really is.
But GPT 4.1 is a black box. It's expensive. So to make this practical, they had to build their own EditThinker MLLM.
Right, and they formulated it as this dual role model. And the way it outputs information is super important. It uses this structured format.
The one that looks a bit like XML with the tags.
Yeah. It's think, then the reasoning, then score, then the scores, and finally answer with the new prompt. This structure forces the model to actually write down its chain of thought.
It can't just guess a new prompt. It has to justify why it's changing it based on a visual critique.
Exactly. And the scores themselves are nuanced. It's not just pass-fail. You have Seri and Sivo, the semantic score.
That's for instruction following, right? Did it do what I asked?
Yes, and did it preserve the parts I didn't want changed? That's rated 0 to 10.
And then there's Earl, the quality score.
Also 0 to 10. And that's purely technical. Does the image look good? Is it natural? Are there weird artifacts or bad blending?
Why are 2 scores so important here?
Because it lets the thinker separate good image from correct image. It can say, look, this is a 9 out of 10 for quality, it's beautiful, but it's a 3 out of 10 semantically because you lost the cat's fur texture.
I see. That lets it make a much smarter decision about what to fix.
Precisely.
Okay, let's get into the training. This is where the magic happens. It's a 2-stage process.
Supervised fine-tuning, or SFT, first. Then reinforcement learning tuning, RLT.
So SFT is the first step. They're using those expert examples from the GPT 4.1 Oracle.
Right. They use that to teach their base MLLM, which is Qwen 3VL, the basic format, how to critique, how to refine an instruction. It's teaching the model the ideal way to think.
But the RL stage, that's what they say, bridges the think while edit gap. What does that mean?
Well, the SFT model learns a perfect theoretical path, but that's not how real editors fail. They fail in specific, messy ways. The RL stage optimizes the thinker by having it work with the actual failures of a real editor, like Qwen Image Edit.
It grounds the theory in practice.
Perfectly said. They use an algorithm called GRPO for this with a really clever multi-part reward function.
Okay, let's break that down. The first part is critic reward.
The critic reward. This is all about calibration. It compares the thinker's own score for a prompt against the expert's score. If the thinker is consistently overconfident, this reward penalizes it until it becomes an accurate judge of its own work.
That's smart. But the second part, run it Dalatur, the edit reward, seems even smarter.
It's the key, I think. It's a differential reward. It's not just, did you get a good score? It's, did your new instruction produce a better image than the last one?
So if the score doesn't improve, there's no reward.
Or it's negative. It stops the model from just generating random new prompts that are different, but not actually better. It forces the thinker to make changes that lead to real, measurable visual improvement.
That is a critical detail. You have to reward the delta, the improvement, not just the absolute score. Okay, but none of this works without data. They had to build this think it 140K data set.
Yeah, and the pipeline they use is pretty impressive. It's all automated. First, trajectory generation. They have the GPT 4.1 expert generate these iterative refinement paths for tons of different tasks.
Up to 5 turns, right?
Up to 5. But then step 2 is the trajectory filter. Another score comes in and rates every single step. They throw out any paths that ultimately failed, and for the successful ones, they cut them off at the highest scoring step.
So the final data set only contains examples of successful refinements.
Pretty much. And then they do this really smart partitioning. For the SFT part, they need clean, high-quality data. So they take 140,000 of these smooth, successful steps for that.
But for RL, you need the hard problems.
You need the struggle.
Yeah.
So they specifically find 10,000 trajectories that had high-score variance cases where it started out really bad, but the thinker managed to fix it. Those messy, high-fluctuation examples become the training data for the RL phase.
That's a very sophisticated way to build a data set. Okay, so the payoff. What are the gains like?
They're significant. On the general editing benchmarks, EditThinker gives a consistent boost. For instance, FLUX.1 context. Its overall score on EditBench went from about 3.4 to nearly 4.0, a solid lift.
But where it really makes a difference is the reasoning test.
Oh yeah, this is where you see the framework solving problems that were basically impossible before. On RiseBench, which tests things like temporal and causal reasoning, the numbers are just staggering.
Give me an example.
The FLUX.1 model went from a baseline score of 5.8 all the way to 14.4.
Wow.
And Qwen Image Edit jumped from 8.9 to 17.8.
That's more than double. That kind of leap tells you you've cracked a real architectural problem.
For sure. This is what lets it handle those multi-step instructions, like the zebra example. Turn it to concrete, keep the stripes, and remove the pedestal. A single prompt just chokes on that.
And the ablations back all of this up. They showed that think while edit is essential. The one-shot rewrite, think before edit, just didn't perform as well.
Right. But here's the craziest part of the ablations. If you did a think before edit rewrite and then started the iterative loop, performance actually got worse.
Wait, what? So giving it a head start actually hurt it. Why?
The theory is that the loop works best when it learns from the editor's raw failure on the original prompt. If you pre-optimize the prompt, you sort of muddy the waters. The thinker can't as clearly see what part of the original intent caused the failure.
Fascinating. So you have to let it fail naturally first. The ablations also show that more thinking helps.
Yep. More turns, better performance. They scaled it up to 8 turns, and the score kept climbing. But logically, the biggest single jump was at turn 2. That first reflection after the first failure is the most important step.
And finally, it's scalable. You can swap out their trained thinker for a bigger model like GPT 4.1, and the performance goes up even more.
Which is great news. It proves the framework itself is general. The performance scales directly with the reasoning power of the MLLM you use as the thinker.
So, to sum up, this work really reframes image editing. It's not one big generation task, it's an iterative reasoning process. And this framework is a wrapper that can give that reasoning ability to any editor out there.
It's basically a high-level planner and a self-correction tool. It handles the hard thinking so the diffusion model can just focus on making pretty pictures. And the authors are releasing the data and the framework, which is huge for the community.
It really is. And it leaves us with a pretty big question. If the power of this whole system is tied directly to the reasoning ability of the thinker model, does this mean the next big race in image editing isn't about building a better image generator?
You're saying it's about building a better MLLM to supervise it.
Exactly. Is the next bottleneck just a continuous arms race to build the smartest possible visual prompt engineer? Something to think about as you plan your next research sprint.